welcome to Chemical Equilibrium. My name is Dr. English. Today we're going to be talking about Le Chatelier's principle, changes in energy. Specifically, we're going to look at energy and changes in equilibrium, changes in energy, a lot of changes here, some walkthrough practice, the effect on a catalyst, and finally some Regents practice questions at the end. Energy changes in equilibrium. If energy is increased, in other words, gained or added to the system at equilibrium will shift so energy is absorbed, in other words, in the endothermic direction. This is indicated by the addition of heat to the system and, more noticeably, a temperature of the surroundings has decreased. And that's really important to notice because remember, when we talk about temperature and temperature changes in terms of equilibrium and we're adding heat, we can't measure the system, but we can measure the surroundings. So if we notice that the temperature is decreasing in the surroundings, that means the system has absorbed it, and that's really important to recognize. At the same time, if energy is decreasing in the system, in other words, lost or removed from the system at equilibrium will shift so energy is released. In other words, in the exothermic direction. This is indicated by the removal of heat from the system, and more noticeably, the temperature of the surroundings has increased. So if we see an increase in the temperature in the surroundings, we know that it's an exothermic reaction and energy has been lost or removed from the system. Changes in temperature. So let's look at an example. Here we have ammonia plus oxygen gives us nitrogen monoxide, water, and heat. So let's say that this is my left and this is my right. And the stress here is an addition of heat. So I'm going to put an up arrow over heat. We have too much heat on our product side. Therefore, we need to have a new point of equilibrium that shows that heat being used up. So we are going to show that heat is absorbed. Whenever you see an indication that heat has been added, that's going to be an addition of heat. Heat is being absorbed, and it is an endothermic reaction. So adding heat and endothermic reactions go hand in hand. In this case, heat is found on the product side. Therefore, we're going to have a shift to the left in favor of reactants. NH3 is going to increase, oxygen is going to increase, nitrogen monoxide is going to decrease, water vapor is going to decrease as a result in this new point of equilibrium. Let's look at another example. So we have the same example as before. This is my left and this is my right. In this case, the stress is a removal of heat, so I'm going to put a down arrow. Just like with concentration, we're going to shift to replace. So if heat is removed from the product side, ammonia and oxygen need to come together in order to replace the heat that was lost. So this is going to be a right shift or a shift to favor products. This is an exothermic reaction because energy is being released from the system into the surroundings. As a result, NH3 is going to decrease, oxygen is going to decrease, nitrogen monoxide is going to increase, and water vapor is going to increase. Let's do some practice. So this is my left, this is my right. The stress here is the addition of heat. So I'm going to put an up arrow over the top of heat. Because we have too much heat on the product side, we are going to shift to absorb some of that heat and form more reactants. So the response here is a left shift. This is an endothermic reaction. The amount of SO3 will decrease. The amount of SO2 will increase. And the amount of O2 will increase. Let's look at another example. So this is my left and this is my right. This time the stress is the removal of heat. So here is heat, it's still on the product side, that's fine. We're going to remove it, so now we need to shift our point of equilibrium to replace the heat that was lost. So the reactants are going to come together to form more products and as a result, replace the heat that was lost. The response here is a right shift. Heat is lost, so this is an exothermic reaction. And as a result of this, the amount of SO3 will increase, SO2 will decrease, and the amount of O2 will also decrease. Let's look at some more examples. This is my left, and this is my right. The stress here is an increase in energy, and that energy is going to be represented as 73 kilojoules. So an increase of energy, I'm going to put an up arrow over the 73 kilojoules. That means I have more energy on my reactant side. Therefore, my point of equilibrium has to shift in order to form more products. So the response here is going to be a right shift. An increase in energy is the same thing as an endothermic reaction. And as a result, my amount of HBr will decrease as we're using reactants to form more products. The amount of H2 will increase, and the amount of Br2 will also increase as we are shifting to favor products and the formation of more products. Let's look at another example. This is my left, this is my right. Now we're decreasing energy. So we're pulling 73 kilojoules of energy from the system. We have to shift to replace the energy that was lost. In this case, this will be a left shift. Energy is released out into the environment from the system to the surroundings, so this is an exothermic reaction. And since we are shifting to favor the formation of reactants, my amount of HBr will increase, my H2 will decrease, and my Br2 will also decrease. Effect of a catalyst. The addition of a catalyst changes the rates of both the forward and reverse reactions equally. There is no net change in equilibrium concentrations. It may cause the equilibrium to be reached more quickly, but it does not. It does not change the point of equilibrium. So this is my original pathway right here. With the addition of a catalyst, we might see the term alternative pathway being used. An alternative pathway just means it's different from the original pathway of the energy equation as the result of a catalyst being added and the activation energy being lowered. Let's look at some Regents practice questions. Given the equation representing a system at equilibrium, so again, like usual, we have nitrogen reacting with hydrogen to form ammonia and energy as a product. Which changes occur when the temperature of the system is decreased? So I'd like you to stop, reread the question, and see if you can choose the right answer. Let's see how you did. Given the equation representing a system at equilibrium, so this is my left and this is my right. Which changes occur when the temperature of this system is decreased? All right, so here's energy. That's representing our temperature because we know that temperature is a measurement of energy. So it is being decreased. Therefore, I have to shift to replace. So I'm going to go from reactants and form products. The answers below refer to changes in concentration of either the nitrogen, the hydrogen, or the ammonia. The first part of our answers all deal with the concentrations of hydrogen. And we know, based on our equation above and how the point of equilibrium has shifted, that the amount of hydrogen and nitrogen are both going to decrease. So any answer that says hydrogen is going to increase is out. 1 and 2 also refer to nitrogen increasing. So we can't say that nitrogen is going to increase, which means 2 is out. The other two talk about the concentration of ammonia, and we know if we shift from reactants to favoring products that the amount of ammonia is going to increase. Therefore, 4 is the correct answer. The concentration of hydrogen was going to decrease, and the concentration of ammonia is going to increase. Given the equation representing a reaction at equilibrium, H2 plus I2 plus heat yields 2HI. Which change favors the reverse reaction? What I'd like you to do is stop, reread the question, and see if you can find the right answer. Welcome back. Let's see how you did. So which change favors the reverse reaction? Okay, so we want it ultimately to be going in this direction. So here's my left, Here's my right. We want this to go in reverse. So will decreasing the concentration of HI make that happen? No, it will not, because if we decrease the concentration of HI, we're going to be going from reactants to products, and we don't want that. We want it to go into reverse. Decreasing the temperature. So if we decrease the heat, we'd have to use some of our products to make more reactants. So, okay, we know one's out. So this is a potential, 2 is a potential, but let's look at the other ones just in case. Increasing the concentration of I2. If we increase the concentration of I2, well, that's going to make more reactants, and it's going to shift the point of equilibrium to producing more products, so that's not going to make it go in reverse. Increasing the pressure, if I look at this, I have 1 mole of H2, 1 mole of I2, so that gives me 2 moles here. I already have 2 moles here, so pressure is not going to affect this system because the number of moles on the reactant side and the product side are the same. So 3 and 4 are out, which only leaves us with 2, which decreasing the temperature, that will shift it towards reactants, and that is our correct answer. What occurs when a catalyst is added to a chemical reaction? So stop, reread the question, and see if you can find the right answer. Welcome back. Let's see how you did. What occurs when a catalyst is added to a chemical reaction? An alternative reaction pathway with a lower activation energy, an alternative reaction pathway with a higher activation energy. Well, we know that's wrong because we want our activation energy to be lowered. The same reaction pathway, lower activation energy, same reaction pathway with a higher activation energy. If you chose number 1, you're correct. So if we have, let's just do a really sad looking energy diagram here. Reactants, wow, that's sort of tilted. Oh well. We know that the activation energy for this original pathway is going to go from here to here. What we need is an alternative reaction pathway. So I need an alternative reaction pathway that's going to lower my activation energy. So instead from being here to here, it's now only from here to the top of here. So what did you learn? We talked about energy and changes in equilibrium. We talked about changes in energy. We did some walkthrough practice. We talked about the effect of a catalyst. And finally, rounded the whole thing out with some Regents practice questions. Need more help? Feel free to contact me. Have a great day.